Hello, and welcome to this webinar. My name is Francois Leclerc. I'm the product manager and head of the PL3D initiative, and I'm joined today by my colleague, Kevin Green. Kevin is an application engineer and a 3D scanning specialist. So I want to welcome you to this webinar. We're here to talk about 3D scanning and how to minimize downtime. Moreover, the reason we're here is to talk about 3D scanning or reverse engineering. And before we get started, I want to let you know that any questions you might have, you may ask through the question pane of the webinar interface. There will be a period at the end where we answer questions. So let's jump into our topic of the day. First question I want to answer is basically, what is reverse engineering? So reverse engineering is defined as a process or a method through which one attempts to understand through deductive reasoning how a previously made device or system accomplishes a task with very little, if any, insight into exactly how it does so. Okay, so this is a basically very complex way to say that it's basically figuring how and why an object is made in a certain way by studying the actual object. Reverse engineering is not a new process, by the way. It goes back to the Egyptians or the Roman army that would improve their military equipment based on observation of property seized from their defeated enemy. The Romans did not have 3D scanners, by the way, but they still managed to get heavy inspiration from other nations. Now, that being said, their galley was not a copy of the Carthaginians, as you can see on screen here, but it was inspired from it. But it did integrate a few modifications and a few improvements, as you can see in the illustrations on screen. So what good is a 3D scanner then? Well, it lets you work faster and with better confidence. It is especially useful with complex and detailed components. Now, before 3D scanning, people used to do reverse engineering this way. They would design a crude part, have it made, test it into their assembly, measure the gaps or the interferences, and correct their design, and then start over. And depending on the complexity of the assembly, it would typically take them up to 7 iterations to get things right. Now, this is a lot of time, not to mention a lot of money from making all these prototypes. This is where 3D scanners come into play. 3D scanner is, simply put, a device that lets you bring existing objects into a virtual environment and use them as a reference. The scanner projects a line pattern onto the object. The pattern is deformed, and the deformation is observed and interpreted into 3D information. And this information is collected in real time and shown on screen. In the case of reverse engineering, the ultimate goal is typically to transfer your scan to a CAD environment. Now, it's not going to do everything for you. You still have to do a bit of work. Reverse engineering still contains the word engineering. You still need to understand how the part will be used, in what context, if it is going to be assembled to what other components. You still need basically to figure what's called the original design intent. Your 3D scan is typically nothing more than a reference or a basic template for your design. Now, in the example that's shown on screen, you can see that the bolt pattern should actually be based on the pressure contact required by the design. So by now you understand why 3D scanners are useful and what they're used for, but what's the difference between a $1,000 scanner, a $10,000 scanner, and a $50,000 scanner? Well, as you can imagine, there are differences in these scanners. Typically on the internal components, the quality of the lenses, the cameras, the electronic devices, the way they're built, the way they're calibrated, and so on. And in the end, these will have impacts on the data quality. Typically, more expensive scanners will have a better accuracy. Now, the accuracy refers to the error in measurement of the part versus the actual scan. As an example, the more accurate a 3D scan is, the more likely that the part designed with that scan as a reference will fit into your assembly. Think of a simple example. Think of a distance between two holes, for instance. Now, if you're 100 microns off or 4,000, well, it's not so bad. But if you're a centimeter off or 3/8, then it's not so good. Now, the differentiation is also the resolution, or the capability to capture finer details, often confused with accuracy, by the way. You typically need a good accuracy to get a good resolution, but you can have an accurate scan without a good resolution. More resolution will actually, you see finer details in the scans, in a scan, for example, holes, brackets, tiny details. Now, more resolution does not necessarily mean better details. Again, higher quality scanners will typically lead to accurate details. And oversampling can happen with poor data quality, meaning you're basically using too many triangles to express a geometry. And so again, something you will get with higher quality 3D scanners. Finally, pricier scanner will usually be better with dealing with challenging surfaces. Think of dark objects, shiny objects, translucent surfaces. These are all things that are typically more difficult to scan and where better scanners will lead to better performance. Now, as a bonus, one important thing to consider is the software tools that are included or not included with your 3D scanner. What tools are you going to have access to? What functions do you need to do your reverse engineering? How stable are the tools provided with your scanners? These are all important factors to consider. As a summary, a pricier scanner will let you work faster and with a higher level of performance and confidence. And in the end, regardless of the price you pay for technology, it should save you time and money. That's the return on investment, the ROI. So all that to say that a $1,000 scanner is probably a good pick for hobbyists and people working on basement projects, while a $50,000 scanner is usually better suited for companies with high expectations in terms of 3D scanning and performance. Now, there's an old saying that goes like, you basically get what you pay for. Now, this leaves us with what we called the entry-level professional grade 3D scanners. And so basically, we're introducing the brand new PL3. Presented a little over a month ago, PL3 is the perfect compromise between price and performance for business interested into getting to 3D scanning. It provides great resolution, more than enough that you'll typically need. Comes equipped with tons of powerful software tools. For people that are interested in reverse engineering, it's also available with PL.CAD, a very powerful bridge to CAD software module that will let you extract valuable information from your 3D scan and transfer them directly to your favorite CAD software. And this is something that we're going to demonstrate today, by the way. What's also great with PL3 is that by keeping it under our program called VIPL, you can get full credit towards an exchange to a Creaform technology, making it a great choice for a first step into professional grade 3D scanning. All right, so let's jump to our main topic today, how to minimize downtime using PL3 and SolidWorks. So today we're going to demonstrate how to perform reverse engineering on a component, a specific component of an electric garbage truck made by Boivin Evolution. So these trucks, they use an auger that's mounted on an electric drive to compact the trash into their rear compartment. So yeah, on screen here, you can see the part that we're going to demonstrate. So this is what we're going to work with. So quite an interesting component in terms of shape. This part is around 5 feet tall. The one we had access to was brand new, so it was on primer. It's made of steel, and as you can see, the end stage of the auger was reinforced with welding material, making it highly uneven. So the part is directly set up on the plant floor on a simple wooden pallet. So we're going to do our setup, put a few targets here and there, and basically start scanning the part directly. So the scanner is basically used as a paint gun and scans what it sees, and we'll progressively make our way onto the entire part. What's also interesting is you can then take a look at your computer, see if you've missed anything, and if necessary, can always go back to the part and keep on scanning until we've captured everything that we need. So this is how it's done. And now I'm going to switch to my colleague, Kevin, who's going to show us what we do with the data once everything is collected. So I'll just make Kevin presenter. There you go.
All right. Thank you, Frank. Hello, everybody. Yeah, so the goal today is to show you what we do with the scan afterwards. We'll not go through the process of the scan. I imported these two into peel.cat, these two scans into peel.cat right away because they were done in two separate scans. We will be aligning them in here in peel.cat and then merging them. So to start off, I'll just hide one of my two scans, make sure I'm working on the right one. First thing I want to do is clean the mesh. By the way, this is output from peel.os, hasn't been cleaned or anything. First thing I like to do is just to select my part and then use the invert tool to get rid of any isolated patches. So I can see that this one was pretty straightforward. Good scan. The other one right here. So I'll be doing the exact same thing. Control, and I can see that there's probably the wood pallet which is touching. I'll still invert and delete whatever I can see here. And then I will zoom in and then just break the link. So I'll use the paintbrush tool. I'll activate the select through. So just cut a couple of triangles here. Same thing at the bottom right here. Click on delete or delete in the software up here. And I will redo exactly the same thing using the connect tool. Select our part and then invert and delete whatever's left. So we got both our parts here. First thing we'd want to do is best fit these two scans together using the best fit option in the software. From here, first thing I could do is try to do an automatic best fit. So the software will automatically try to put them together. This rarely works in a symmetrical part. So this is symmetrical, I mean, on the rotation. So we'll just give a little help to the software by using point pairs. So we'll use a 3-point. So it starts the best fit correctly. Here we just click pretty much anywhere. It doesn't have to be exactly at the same spot. It's just for the software to start off the best fit in the right orientation. So we can see the shadow here. I'll start the best fit. And that should be good. So once this is aligned, then we'll go on to merge both scans together. So we'll be working on one mesh. I will not do the merge per se in the software because it takes a couple of minutes and don't want to be causing downtime here. So we got our alignment, both meshes together, hit OK, and then we would use the merge function here. And then click on both my scans and merge them both together. And this would end up being our file right here. So yes, I cheated a little bit. I created my entities beforehand just to make sure everything works good. And there are some things I will not do live just because it's time consuming. Before we talk about reverse engineering this part, most important step here would be to align it. So place the origin at the right spot of the part. Why is this important? Well, especially for a part like this, which is rotational, meaning it's going to be mounted on this side here, and it's going to be turning. Maybe at low speed might not cause any issues, but high speed parts, we want to get that exact axis of rotation. To do so, first thing I do is create a cone, because we can see this is a conical shape. So I'll create a cone. It's going to extract the axis, which I will be using to constrain, let's say, the z-axis on the part. So that would be my first entity. So the software is thinking, just because there's a lot of triangles, fitting that cone in there. So once that's done, I'll just cancel that because I already have it in my tree. The other entity I will be using is a plane at the bottom. Now, my educated guess is that the part is going to be mounted on this plane here. Why I say educated guess is if I select this surface right here, again, this would be something I would confirm with the customer, make sure everything is right. I can see, you know, standard dev is a little high. I always look at these two numbers when I create entities, specific entities. So high standard dev, that means this is probably not machined. If I undo my selection and do my selection on the mating surface right here, so I can see that the standard deviation is really, really low. So this just gives me a cue that it's probably mounted on this circle. So I'm going to be using that plane. Again, hit OK, but I already created it, so won't create it again. And then we'll go into alignment. So for the alignment, I will be using the align tool right here. If you click on it, I know it says manual alignment. The first thing that happens is the software drops the origin at the center of mass of the part. So we will not be using that. Again, I will be using the entities I created. So the cone, I will specify I want it to constrain the z-axis. I'll just flip that so that it's in right orientation. So my z-axis is constrained on the axis of the cone. Second entity I'm going to be using is the plane, where I will lock the, sorry, do I have the right plane? Yeah, I do. So there seems to be an issue here. I don't know why, but it locks the plane in place right here. So my XY, my X and Y origin are locked on the plane I created, and the Z axis is locked on the axis. So from there now, the idea is to create entities to help me reverse engineer the part in SolidWorks. Now, when we talk about reverse engineering, there are a couple of branches. Two of the main branches would be as is and design intent. As is would be, I want the exact same thing with the exact same defaults or defects in the part. So as is, we would even try to reproduce these welding lines. Well, maybe not, but you get the idea. Like all the defects you could see here in here. We will kind of be doing that today. The other option would be design intent, where we want to make everything nominal. So let's say if I measure a hole in here and my measurement gives me 2.04 inches of diameter, I will put that hole at 2.00 inches. So that would be design intent, where you force the part to be machinable, let's say. All right, so from here, first thing I would create is the helix here, the spiral. So the way I chose to do it, again, there are many ways of doing this. I just chose one to show you the functions in the software and how we can do that as is. So here I created two splines that follow the auger all around, all the way to the top. What I used here is the spline tool, or the curve tool, sorry. And then instead of fitting the curve on the mesh, so this will have the consequence of, you know, following the mesh and all the bumps. I just use a free, like a freeform spline, where I just selected points on the edge of the mesh, and then it created a 3D spline in space. So I'll just wait for the function to pop up. And from there, I will transfer these 3D splines into SolidWorks. So yeah, sorry, here, instead of using the traditional like fit on mesh, so fit on mesh will have not the consequence, but if I use this here, you're going to see the bends in the spline. In this case, I wanted something pretty smooth, so I just use the free curve and added these two curves. So from here, I can select these two curves and send them to SolidWorks. It's going to take just a few seconds right here. So I do have my two curves in space. And from here, let's say I would want to recreate that. Again, I'm doing an as-is design. Design intent, I would probably create a curve like a helix spiral, give it the right pitch and the right diameter, and that's going to give me like a perfect part. The goal here, again, was to show you how to use the scan to make an as-is reverse. So with my two splines here, what I can do is create a 3D sketch, and then just close the sketch using a line. So I just snap the line on both endpoints. Do the same thing at the bottom here, snap it there, snap it here, escape, and I have my 3D sketch. So from, I always forget to close it by here. So from here, what I can do is create a surface. I'm going to go in the surface functions, and I will fill the face. I select a sketch, so it's going to create a face with the part I just created. So check mark. And then from there, my surface, what I can do is thicken it. So if I looking for thicken my surface, I'm going to select my surface downwards, and let's say this is a, I don't know, 1/4 inch plate. So I'll put 1/4 inch thickness, and there we go. So we got our auger, I don't know how to call it, pattern or pitch from the bottom to the top in the right orientation. And there we go. So it took care of that central part. Now the other thing we could do is the center part. I created a cone, maybe not the best way, but it was the fastest way to show you guys. The best way, in my opinion, would have been to create a cross section, and then using a cross section, I could sketch around the cone and then revolve it into SolidWorks. The reason why I didn't create it now is just because it's going to be time consuming, and I want to show you the most functions in the software. So from here, I'll just transfer my cone using the transfer tool, or we could use the shortcut up here. So the neat thing is, and if you guys understand the workflow, is that you work in SolidWorks, go back to peel.cad, create your references, send them back to SolidWorks, and they will open in the right part. So from here, I have my cone. The other thing I want to do is I want to send my plane. I created a plane on top here just to know where the cone is supposed to stop. You can see my cone is shorter here, and I wanted to extend it down here. So what I'll do is, forgot, did I send that plane? No. So I'll send the plane using the shortcut. So we can see the plane right here. What I'll do is I'll just edit the cone. I could probably extrude it to a plane, but I'll use another function. I will just make it longer and then use under the features, I'll use the intersect tool, little tool I like to use a lot. Intersect, and then just click on the part I want to delete. And now I'm sure that the height of the cone is correct. All right, so I got my cone, I got my spiral. From there, you can create the bottom part, which is the cylinder. Again, I just use a cylinder function. I could either, and then make sure my selection is correct. So go around and make sure it's decent. Now this surface is pretty small. What I can do is give it a constraint. So orientation, I can say I want you to be perpendicular to my cone axis. So it will fit this like that. So okay that. Now from there, I can take my cylinder, transfer it to SolidWorks. And then I got the bottom part. Something else I can show you is, let's say the bolt pattern here, I will not be recreating it all, but I can show you how I would do this. I'm going to use the orientation to make sure my cylinders are perpendicular to the cone or in the same orientation. Diameter, see, I can see 27.125. That kind of makes sense. I'm not sure if this is a metric or imperial part. The other thing I'm going to do is give it a longer length. So I'll put, like 25 or even more. I can put 50 in here. And from there, I will okay that. And I don't know if you guys noticed, but these are smaller holes. I'm going to do the big holes because they probably have all the same diameter. Okay, that. Same thing here. Okay. And another one here. Let's say we do all these 4 holes. I can then select them in my tree. So my 4 cylinders, transfer those to SolidWorks. Again, I know I'm repeating myself, but that's kind of the workflow. Work a little bit on your mesh, create references in peel.cad, send those to SolidWorks, continue your part. And then depending on what you want to do, well, you go back, peel.cad, recreate references, and then send them back. So I got my 4 cylinders. What I can do is easily use the intersect. So I don't have to worry about the diameter of these holes because I already specified them in here when I created them. So what I'll do is use the intersect tool, select my 4 cylinders and my base plate, intersect, and then go ahead and just delete the inside. That's the long part. And remove the unwanted section. So there we go. And then we got our 4 holes. All right. All right, so from there, so I did the base plate. Something else we can do is, let's say, cross section to create these fins at the bottom. So let me just hide everything here. Not sure which cross section, not this one. Good thing also, which I didn't do, should have done, is renamed my features to understand where they are and not try to look at them in my tree. So from here, I can send my cross section. So transfer to SolidWorks. Again, I created this cross section to have the outline of the fin at the bottom. So I got my sketch. If I edit my sketch, I'm going to use Control-8 just to be perpendicular. I will select all of my sketch here. So all the lines that have been created from the cross section, and I'll just use those as construction. I could use the sketch directly, but in this case, the sketch is not closed. You can see there's a small bend, not bend, but curvature in here. Lines, there seems to be a double surface. So what I'll do is I'll just sketch over the sketch, make sure everything is nice and clean. So I'll just, sketch like this, create a few lines, and then use the trim tool to have a closed surface. Now I won't be doing the whole sketch as it will be redundant, but what I can show you is the already not finished, but advanced version here. So we can see my sketch, which is here. So if I maybe edit it to show you guys here, sorry, Control-8 to be perpendicular. So I just created lines, trimmed them, make sure I have a closed surface, and then I use this sketch to do a an extrusion, and then from there I created a pattern, and skipped one instance, which is here, and that creates my fins at the bottom. All right, any questions, Frank? No, probably not.
We do already have a few questions, so I guess we could start. And I don't know, Kevin, if there's something else you wanted to show, but
oh well, yeah, I can continue like on and on, but yeah, the center part.
Yeah, we got a few questions, so I guess we could answer them, and I'll let you go after. So first question is, wouldn't it have been faster to recreate the holes at the bottom using a cross section and creating circles?
Faster, I would have a tendency to say no. The reason why is when we do use a cross section, maybe I can demonstrate it. It should not take too long. Let's say I have my plane, just to make sure I have the right plane. I'm going to create a cross section. So first answer is, well, it depends who scanned the part. In this case, it wasn't me. I mean, he did an okay job, but he missed a couple of spots. And the other thing is, when we create a cross section of holes, the software creates splines and not circles. Okay, so these splines will not necessarily be perfect circles. So I will have to go back and redraw them in SolidWorks, or at least draw a circle over the spline. So I find it faster to use cylinders and then use the intersect tool. If that makes any sense. I just wanted to show you if I cut it here and click on OK, again, I don't know how many sections we have, but if I hide the part, hide the scan, and then show you just a cross section, you'll understand that even if I zoom in, you can see that this is not a perfect circle. So I'd have to go back and sketch every circle, which comes down to doing all the cylinders at once. So I'd rather do the cylinders.
Okay. Interesting. So there's another question here. Yeah. Oh, I guess you're going to show that later, but yeah, there's someone asking, can you bring the STL mesh into SolidWorks?
Yes. Oh, sorry, wrong part. So I did transfer it, so it is here. So if I show my STL here, you'll see that. Sorry, it's a little, SolidWorks is not 100% made to play around with STL, so sometimes it's a little laggy. We can see here that, doing the center part here, I'm pretty straight on. I'd be curious to see my deviation, but it's pretty good. Yeah, so we can compare and see our reverse as we go by importing it in SolidWorks. depending on the size of the mesh also.
Nice.
Any other questions, Frank? Or?
I think you kind of answered that one already, but yeah, there's someone asking if you look at the sketches in SolidWorks 3, would they appear as fully defined or underdefined?
Oh, so when I transfer a sketch?
That's yes.
Yeah, so when you transfer a sketch, again, I might be repeating myself, but when you create a sketch, it really just creates splines of the cross section. Sorry, so all these here are splines, and they will be fully constrained, yes, in the transfer here. Sorry, I'll just hide my mesh because it's lags too much. It will be fully constrained, but only as an anchor, meaning there's no dimensions. It's really just an anchor in space. Forgot how that one's called. Maybe I can try to show you, or maybe in my other part. So if I go back to the sketch here and delete, let's say, my line I created, and then undo the for construction, you can see that my sketch is black, meaning it's fully constrained, but it's only fully constrained because there's an anchor on the lines.
Oh, yeah.
You can see fixed here.
Good.
Any other questions?
Not for now.
Okay. So another, I don't know if I mentioned it, another way of like, not the design intent, but sorry, yes, for the design intent instead of the as is reproduction of the part, what I could have done is created a helix and spiral here. What this does is it really creates a perfect spiral. Probably in 2 steps I would have done it here because we could see there's not the same pitch from here to here and here to here. And then that would have created a perfect spiral. In this case, I would have probably just used a scan to overlay it to make sure I get the right pitch or close to the right pitch, because this one probably is made by hand, bent by hand, and then welded, so it moved a lot. So if we want to do an as is reproduction, I wouldn't necessarily use this helix because this is too, let's say, perfect. Yeah, from there, I mean, it's just a matter of creating our references in here in peel.cad and then sending them to SolidWorks to make sure we get that reverse correctly. The other part I did was created a cross section using this plane here, which somewhere in here, yeah, cross section. Again, I just transferred that cross section in here for this part. I sketched for the other side. I sketched over the cross section that I imported, and then I just extruded the part. Make sure I get the right cutout. And if, I mean, where this would come in handy, I don't think I did it, but oh yeah, I did it with the intersect. We could get the right cutout so that the part fits on the tubular, let's say, center. What I'm trying to say by that is we can clearly see here, if I close all the entities, that this part is, there seems to be a little round, but sometimes people will just cut that straight and try to fill the gap with welding. But using the intersection here, we could find the exact curvature so that the cutout could be done on a plasma machine or
plasma cutter or something.
Yeah.
Great. And yeah, I'm actually being told by someone from the audience that using features like cylinders make sketches with dimensions in SolidWorks. So
yes, sorry, I didn't think about that, but yes, when you use native, not native, but when you use the entities here, like 3D, I'd say entities, well, the 2D entities, you can also give them the right dimension. But as I did here, when I use the cone, if I go and edit the cone, I can either edit the 3D function, so the native function, or if I go into the cone sketch here. But yeah, no, I think I was correct. There is a fixed arc here.
Mm-hmm.
So I could just delete that and then use the smart dimension and give it the right diameter.
Nice. So it's probably 302 in this case. Great. Yes, excellent. Great. So I guess this basically covers what we wanted to show you today, and we're going to move on to the question phase of this webinar. Let me turn on my camera again. And yeah, so again, if you have anything specific you want to ask, you can ask it through the question pane. I know some of you already sent a couple questions. I still got a few open ones we didn't get the chance to answer, so I'll start right away, and feel free to post in your other questions. First one, Kevin, I think I'm going to ask you. Okay, yeah, this one's interesting. Is it better to do several scans and merge them afterwards, or do a single scan directly?
Honestly, that depends on your, it's directly in relation to your computer, meaning if you have like a decent, powerful computer, you can withstand more scan. I have a tendency to always try to do one scan, but honestly, I think the best way to do it is to cut up your project in different scans and then merge them together after, either in peel.os or in peel.cad. And what we have to think, what we have to remember here is most important part is to have a good part setup, meaning you have to think about that before you start scanning. Hey, I'm looking at this auger. I'm gonna do 2 scans. I have to make sure I get a good overlap from both sides to do the merge.
Very good. Another one, I guess, for you, Kev. What's the interest for peel.cad if you can import an STL in SolidWorks?
Good question. Interesting question. I mean, yes, you saw that I could import an STL in SolidWorks. The reason, I mean, the difference between peel.cad and SolidWorks is that peel.cad is meant to work with STL files. SolidWorks has I mean, we can do it, but you are very limited, and the software is not made to work with meshes. I don't know if you guys noticed, but I switched the display of the mesh in SolidWorks just because my SolidWorks was lagging a lot, and I didn't have like a huge scan, meaning I think we had like 5 or maximum 10 million triangles. So if you go above that, I mean, SolidWorks has trouble showing all the edges. The other thing is, yes, you can create, I think, certain basic references like planes where you can touch the scan in SolidWorks and create a reference plane, but nothing compared to peel.cad where, I mean, we have literally, maybe not all the functions, but everything we can create in peel.cad, and it's an easy, it facilitates the step between scanning and CAD modeling.
Great. Another question here. How far is the distance that the scanner is from the part while scanning? And this one I can answer. So the usage distance with a PL3 is between 250 to 550 millimeter. So that's 9.8 inches to 21.7 inches. Reference distance is roughly in the middle. So that's around 400 millimeter, I guess around 15 inches or so. yeah, so these are the reference distances. Okay, there's a question here about pricing. How much does the scanner and software cost? I already have SolidWorks. That's good. So the scanner by itself, just the scanner is $8,500 US, and along with the peel.cad option that you've seen, it's $12,000 US. There is that. Yeah, let me bring another one up. How is Peel3 different from previously made Peel3D scanners? So you want me to answer that one, Kevin? Or?
Yeah, sure, go ahead.
Okay, yeah. So Peel3 is basically has been designed from the ground up. So basically everything into the scanner has been changed and reviewed. So it's completely different from the previous generation of Peel3D scanners. So it deals a lot better with challenging surfaces, with darker surfaces, and especially with intricate objects as well. So yeah, it is significantly different from the previous generations. Let's see. Do you need the reference dots? I could see them with the auger being scanned. You want to go ahead and answer
Yeah, I
that
can
one?
answer that. You don't have to use reference target. We call them targets, but dots or whatever you want to call them. You don't have to use them. It's just easier, especially on a big part like that and on a not symmetrical. I forgot what the term is in English, but the auger has the same section going all around. So the scanner needs to know where it is in space. So using just a couple of targets will help it. But no, you don't have to use targets with the Peel 3.
Okay. Sorry, there's many questions. I'm trying to go through them to all of them. Okay, let's see this one. What is the pre-processing process to be done from scan data before we start to model the part? How is the mesh done?
It's called live meshing, meaning I don't know. I mean, I won't necessarily show it, but while you scan, it automatically builds the mesh. So there's no going from a raw data to point cloud to then triangulating into a mesh. While you scan, what you see is what you get. So you scan, creates the mesh. The only step I didn't do, well, I didn't really not do any steps, but in peel.os, we got our scan. And then at the last step is send to peel.cad. And that's where we started the demo. So meaning I didn't do anything in peel.os. The only thing that was done was it was scanned by our colleague, and then he sent us the file where we used peel.cad.
Yep. Yeah, and there are basically tools in peel.os to clean up, align, finalize your scan directly into that software. But all these tools are also available into peel.cad. And so if you're planning to do reverse engineering as we were doing today, you can do as Kevin explained and do them directly in there. I'm trying to see here. There's a question about the minimum requirements for the laptop. So scanner is basically built to work with a regular off-the-shelf laptop. You still need a pretty decent computer, but usually well, the important things are to have one that is equipped with an NVIDIA GPU. That's important, with 6 or more gigs of RAM. And you also need ideally an i7 processor with a decent clock speed. and a decent amount of RAM. So I'd say, at least 16 gigs, but you should probably go for 32 or even 64. Especially since nowadays it's getting more and more accessible and affordable. So these would be our recommendation for laptops. Yeah. So I think that concludes our presentation. So I want to thank you for joining us today and your participation. And there will be a recording of this presentation available, so you should receive the link in a few days. So again, thank you, Kevin, for being with us, and wish you a great rest of your day.
All right, thank you, everybody.